Hello everyone, this is Group 16 and I am Suraj Sahoo. I along with Harsha will be explaining the concept of ensemble learning, especially the technique of boosting. Ensemble learning is a very standard technique and very powerful and used in multiple areas, and it performs a lot better than the traditional learners. So ensemble learning is also known as committee-based learning, but we'll call it ensemble learning for our purposes. Throughout this video, we'll be calling it ensemble learning. So the main idea behind ensemble learning is to combine multiple base learners. So you have base learners 1, base learners B1, B2, and so on. And your idea is to combine these B1, B2, and Bn to a classifier B, which performs better than all of these classifiers together. So these base learners can be your decision tree or even neural networks, and or even any other learning algorithm. So if the ensemble methods use a single base algorithm, then it is known as a homogeneous ensemble. And if it uses multiple base learners, then it is heterogeneous. Now the strength of an ensemble method is in the fact that it takes supposedly very weak learners. The concept of weak learners and strong learners is something that I will touch a little later. But for now, just understand that these are learning algorithms that are doing not that are not doing very well. That are just only slightly better than the random guessing. So the ensemble method takes weak learners and it combines them to create strong learners. So that is the strength of this learning approach. It doesn't matter how weak these learners are. Together, they can become very strong learners and even outperform the traditional good learning algorithms. So now let's understand what these terms actually mean. So a weak learner is colloquially a model that performs slightly better than a naive model. So, for example, in AdaBoost, it is which is a boosting algorithm. It is quite common to use decision stumps as the weak learners. So, a decision stump would be an example of a weak learner. More examples are as follows. So if you have uh, k nearest neighbor with k equals 1, operating on operating on one or a subset of inputs. Similarly, multi-layer perceptron with a single node operating on one or a subset of input variables. Naive bias also operating on a single input variable. Now, strong classifiers, strong learners, are those that achieve arbitrarily good accuracy. Okay, so these models perform very well compared to a naive model. Examples of strong learners are as follows. So each of these perform well if their hyperparameters are tuned to the problem. All of these are strong learners. So the two most popular ensemble methods is bagging and boosting. And in this video, we will only be talking about boosting. So let's try to understand what this is all about. We will try to understand boosting by understanding a particular by two different algorithms. Uh, One is the adder boost and one is the gradient descent boosting. Uh, so let's start. Okay, so now we'll be talking about the most popular boosting algorithm, the adder boost. So this algorithm is due to, oops, this algorithm is due to Freund and Shapiro. Um, so what we are trying to do is is a sequential application of the weak classification algorithm to repeatedly modified versions of the data. So we are trying to produce a sequence of weak classifiers GMX, okay, at each step M. Okay, so M is signifying this step number. So we want to produce a sequence of weak classifiers GMX, which works well on a certain section of the data, suppose, and Combining these weak classifiers, we will we will also associate a vote to them. We will have a, so this is called a weighted majority vote. Okay, this concept is called the weighted majority vote. We will not only combine these weak classifiers, but we will also combine them in uh, with weights associated to them, so that those classifiers which are doing well will have their votes increased, and so that they have a more influence on the output, and those classifiers which are underperforming, they'll have their votes decreased. So uh, the basic so the formula that we will be using for this uh, for this whole concept is given by this expression. So these alpha m's are uh, the votes associated to the GMs, and these affect the total uh, total outcome by influencing those V classifiers which are doing well. Okay, so the entire process happens in steps. So in each step we associate a number of weights, W1, W2, Wn, to the n training samples. N training samples. This is happening at every step. Okay, x I y I from 1 to n. Okay, so at the first step, wi is just taken to be 1 by n. Everything is equal and everything is 1 by n. So when we are having a weak classifier g1x, which is uh, which is taking all these data points and producing an output, so it must have certain regions which it is classifying incorrectly. So suppose this is the area that is being incorrectly classified by g1x. Now what Adabos does is it increases the weights of these misclassified data points, and it decreases the weights of these the correctly classified data points. So not only are we giving votes to the classifiers, we are also changing the weights associated with the training samples at every step. So now this modified data set will be used for the next step. So this motivates the following schematic diagram. So we have a training sample which is fed into the first weak classifier, and this classifier misclassifies certain sections of it and correctly classifies certain sections of it, and it has accordingly, as we just discussed, the weights of this training sample is modified. So the misclassified ones are increased and the correctly classified ones are decreased, and this modified sample, so this training sample is now changed into a modified weighted sample. Let it be 1. So this is the first modified weighted sample, which is then passed into the weak classifier induced in step 2. and again it misclassifies certain parts and it correctly classifies certain parts, and the same thing continues. So this is the modified weighted sample 2, this is G3, and so on. So now this is the final one. This is m minus 1, and this is GMX. Now each of these V classifiers are now fed into GX. By the formula given in the previous discussion. So now I'll write down the general algorithm. So this is the algorithm for the ADA boost. Uh, so we'll try to understand how this works. Now, as we said, we will initialize the first observation weights as 1 by n. Now, for every for every step, what we do is we we fit a classifier GMX to the training data using the weights WI. So as I said, and you could even see from the schematic diagram that this is an important step. Now we compute the error, which is just uh, the amount of which is just the sum of weights that the misclassified elements are contributing. This is the I is the indicator function which gives you 1 if it is being misclassified and 0 if it is not. So we are only counting those weights which are being misclassified, which correspond to the data points which are being misclassified by GM. Now we will compute alpha m. This is given by log of 1 minus error m by error m, error at step m. So this makes sense because if we have a classifier which is doing a better job than just a coin flip, then this error rate would be greater than 1. Um, so that means this entire thing would be a positive quantity, which means that that particular classifier would have a better influence than the others. Uh, it would have a positive influence. So 1 minus the error by the error, this is greater than 1 only when the error is greater than half, which is better than a coin flip. I mean, which error is less than half, which is better than a coin flip. I beg your pardon. Now you set Wi to be the Wi exponential of alpha m y I y I gmxy not equal to gmxy. So this seems like a very complicated expression, but it actually isn't. It is just a fancy way of saying that whenever we are making a mistake, we are increasing the weights by exponential of alpha m, and we are storing it again in the place of wi. So we are modifying the weights by a factor of exponential of alpha m whenever there is a misclassification. That's all it is. And now the output gx is given by this formula. So that is more or less it about the ADA boost.
Welcome to this introductory lecture on gradient boosting, and since you made it this far into the video, I hope you understood what boosting is, and we'll quickly transition into what gradient boosting is from our knowledge of boosting. Gradient boosting was first introduced in 1999 by Jerome Friedman. You'll find his paper. It's called greedy function approximation of gradient boosting machine. And this was the paper where gradient boosting was first introduced. So I'll go over how gradient boosting differs from the general boosting framework, and hopefully by the end of the video you'll understand why the term gradient is coming into the picture. Even though it was introduced in 1999, still probably one of the most popular ensemble methods in 2021, and its variants are among the most popular ensemble methods used in data science competitions. Okay, so I'll start off with gradient boost. I'll start off with the general algorithm of gradient boosting. The key difference in gradient boosting is that we now have the power to choose a loss function. And instead of just plainly calculating residuals, we can do something a bit more sophisticated, as you'll see. So we'll input a dataset D. You can assume this is a regression dataset. It really doesn't make much of a difference, but regression dataset is easier to think about. So this L will be a loss function, and you'll see how we smoothly integrate this L into the boosting algorithm. So if we recall in the normal boosting algorithm, the first step is to train a weak learner on the dataset D, and this is exactly the same in gradient boosting, but there's a specific model we train, and it's in fact a constant function. And how do we get this constant function? We'll minimize the sum of the loss we'll minimize the total sum as follows. So we'll denote f naught. We'll let f naught be the base learner, and f naught of x equals arg min gamma summation I equals 1 to n L times L of yi times f of x, f of y times gamma. So as you see here, f naught x, so f naught x is just a constant function, and we'll iteratively try to improve upon f naught x, just like in the general boosting setting. Next step is to obviously create a new model called f1, but how do we do this? We'll calculate what are called pseudo residuals, and when I take an example of a loss function, a specific loss function, you'll see why these quantities are called pseudo residuals. But till then, just assume they perform the same role as residuals you know in the general boosting algorithm. So how do we calculate this? For each I in 1 to n, so for each data point, Ri equals negative of del L yi naught xi by del f naught xi. For I equals 1, 2 up to n, basically for each data point. So if you remember what happens in boosting, the next step is to create a new dataset d1 equals xi ri equals 1 to n, and we'll fit a base learner to d1 so that h naught be trained on, be the result of an algorithm training on d1. So this again could be the same as this again is, it could be just a decision tree, it could be a linear regression, whatever model, whatever base learner you're choosing to perform boosting upon. And the next step is to, if you remember, the next step in boosting is to add f naught and h naught using a step size or a learning rate. And typically in boosting it's just a small value, but we have a specific way of choosing a learning rate now, and we'll denote this by gamma. So gamma naught equals r gamma equals 1 to n. Plus gamma times h naught xi. So in boosting, this alpha naught would have been probably a small value that you fix at the start before you start running your algorithm. But in gradient boosting, there's a specific way of choosing your learning rate at each step. And for the first step, it's the gamma which minimizes this value. And this value is you can think of it as the total loss of this. If you think of this quantity as a new model that depends upon gamma, we're trying to minimize the total loss that this model commits. We're trying to minimize the total loss this model commits, and we're choosing the gamma which commits the least error. So after n steps, let's say, the model would look something like this. And entirely the same as in the boosting algorithm. After m steps, this is exactly how it will look, but usually there isn't any specific way of choosing the learning rates, but at each step we're choosing a specific learning rate, and this in fact is a greedy step, because our choice of gamma naught is minimizing this loss. So making the greedy choice at every iteration, and is in fact the reason why the original paper of gradient boost is called a greedy function approximation. So I'll take an example of a loss function, and hopefully you'll have a clear idea of how to remember pseudo residuals and why they're called pseudo residuals. Suppose a loss function is equals half of yi minus f of xi whole square. So if you remember what a pseudo residual is, it's del L yi f of xi del of xi equals minus, right? So in this case it would be yi minus f of xi, and this quantity should really be familiar to you, and it's in fact what we call a residual. And you would have come across this term if you've gone through the boosting algorithm. And it's actually pretty obvious why this quantity is called a residual, because in a sense it is the leftover value. It is the actual value minus the predicted value minus the actual value. So it's the actual value minus the predicted value. And this is in fact why for a general loss function, this partial derivative is called a pseudo residual. And for this specific loss function, in fact this is the most common loss function, squared error. And if you come across logistic regression, we use a similar loss function, the mean squared error. The reason we're using a half here instead of 1 by n is so that when we take the partial derivative, we get exactly the residual as our pseudo residual. Our I would exactly be equal to the residual. If it was 1 by n instead of 1 by 2, it would be slightly different. Yeah, I'll also demonstrate what happens, what our initial f naught is in this case. If you remember, I'll rewrite what f naught is. I've been gamma. So in a sense, gamma is, you're given a choice of one number, and if you're given one number, you're trying to find one number which gives a good idea of all the. So yeah, so gamma in fact is, in this case, would just be gamma sequence I equals 1 to n, my loss loss function in this case equals yi minus gamma whole square by 2, right? And you can verify after differentiation that f naught x achieves its minimum at sorry, this quantity achieves its minimum at this quantity achieves its minimum at okay, I'll do it for you. If you differentiate this quantity with respect to gamma, you have sigma I equals 1 to n minus yi minus gamma, and if you're familiar with basic calculus, you should know that to find a minima we must equate the derivative to 0. So once we equate it to 0, there's n gamma equals sigma equals 1 to n yi, which means gamma equals sigma I equals 1 to n yi by, and this is nothing but your mean. So if this was a choice of loss function, our first prediction would just be the constant, would just be the average of all the yi's. And this makes some sort of sense because we're trying to find one yi, so one gamma, which represents all the yi's pretty fairly. So this loss function is sort of the originating point for all the terminology here, and hopefully you've understood why pseudo residuals are called what they are. And really the only difference in boosting and gradient boosting is the difference in the way pseudo residuals are calculated. In our case we use the partial derivative of the loss function. So this is really the key step, and this is the reason why the name gradient is added to boosting. Thank you.